Okay, this is exam 3 for Physics 101, Fall 2010. Number 1, it says a tire is placed on a balancing machine in a service station that starts from rest and turns through 3.2 revolutions in 2 seconds before reaching its final angular speed. What is angular acceleration in radians per second squared? Alright, our first thing, this is our angle theta, and we want to convert that into radians. So 3.2 revolutions. In 1 revolution, there are 2 pi radians, and that's equal to 20.1 radians. See, my revolutions cancel, and then I know that theta is equal to omega naught t plus 1/2 alpha t squared. Omega naught is 0 because it says that it's initially at rest, and so theta is just equal to 1/2 alpha t squared. If I solve that for alpha, which is the angular acceleration, I get alpha is 2 times theta over t squared, 2 times theta over t squared, which is 2 times 20.1. T is 2 seconds, so that's 2 squared. So it's 20.1 over 2, which is 10.05 or 10.1. So that answer is B. A tire 1 meter in diameter is placed on a balancing machine where it is spun so that its tread is moving at a constant speed of 20 meters per second. A small stone is stuck in the tread of the tire. What is the acceleration of the stone as the tire is being balanced? Well, it says that it's spun at a constant speed of 20 meters per second. So the tangential acceleration is 0. So we need to figure out what is the centripetal acceleration. We call this AR, and it's equal to V squared over R. So V is 20, so it's just 20 meters per second squared over R. That's the radius. It was 1 meter, so it's 0.5 meters. 1 meter is the diameter, so half of that is 0.5 meters. So let's see, that's 400 over 0.5. That is 400 over 0.5, which is equal to 800 meters per second squared. So that answer for number 2 is A. It says Chad and Kaiser are spinning on a merry-go-round. Here's our merry-go-round. Chad is on the outer edge. Kaiser is on the inner edge. Which one has the larger centripetal acceleration? Well, centripetal acceleration, again, is V squared over R. But we know that V is equal to omega R. Well, look here. So Chad has a bigger V. Alright, but he also has a bigger R. So it's not clear immediately that he has a bigger centripetal acceleration. But if we consider that V is equal to omega R, and we substitute that in, we did this in class, substitute this in for V, I get omega squared R squared over R, which is omega squared times R. So omega, the angular speed, is the same for both of them. So the one with the bigger radius has the bigger centripetal acceleration. So that is Chad. That answer is A. Certain light truck can go around a flat curve having a radius of 120 meters with a maximum speed of 25 meters per second. With what maximum speed can it go around a curve having a radius of 75 meters? Okay, well, it's on a flat curve, and we know then that the centripetal force is equal to the static frictional force. So that is mv squared over r is equal to mu times the normal force. Mv squared over r is equal to mu. Since it's on a flat road, the normal force is equal to the weight, so that's just mg. Now, initially we know that with a radius of 120 meters, we can have a speed of 25 meters per second. So from that we can calculate what is mu. Our masses cancel. I want to figure out first what is mu. Two-step problem. So first find out mu. That's v squared over g times r. And using these first numbers, it's 25 meters per second squared over 9.8 times 120, or 120. And that is equal to 0.53. So my coefficient of static friction is 0.53. And then I want to take the same equation and solve it for V. So I'm going to solve this for V. And V is equal to the square root of mu gr. Because now on that same road, I want to know how fast can you go with a curve of 75 meters. So it's the square root of 0.53 times 9.8 times r, which is 75 meters. And that gives me 20 meters per second. So that answer for number 4 is A. This figure shows a truck on a banked curve and all the force vectors acting on it. A driver can safely drive at a higher speed on a banked curve rather than on a flat curve. Which of these reasons is the correct explanation of why this is possible? All right, let's just look at them. The normal force for the car on the banked curve is less than on a flat curve. That's a true statement, but that's not why it can drive faster, because if the normal force is less, then that also means that the static frictional force is also less. So while it's true, it's not the correct answer. The weight of the car is greater on the banked curve than on a flat curve. No, the weight doesn't change at all, because the mass doesn't change. On a banked curve, a component of the weight acts down the slope, and thus increasing the centripetal force. We'll come back to that. That's the right answer. Let's just look at this last one. The static frictional force for the tires on the banked curve is greater than on a flat curve. Same as part A. If the normal force is less, the static frictional force is less. So the only one left is C, and that is that a component of the weight acts down the slope. So if we look at this force right here, it breaks into two components. One component goes in that direction, and one component goes in that direction. It is this component that adds to the centripetal force. So the centripetal force is equal to the static frictional force plus the x component of the weight. And that's why you can go faster around a banked curve. An object is traveling in a counterclockwise circular path. At the point shown, the string holding the ball in the circular path is cut. What is the path that the ball follows after the string is cut? Alright, well, this is an application of Newton's first law, that an object will continue in motion in the path that it's traveling, in fact, unless some force acts on it. And the reason that the ball is going in a circular path is because you have the tension in this string that's pulling it into the circular path. That's your centripetal force. If you take away that centripetal force, the object is just going to travel in a straight line. So the answer is B. The speedometer on my bicycle measures the angular speed and converts it to linear speed based on the radius of the wheels, which I input. Suppose I input a radius that is smaller than the actual radius of the wheel. Which of these statements will be true? When my computer makes this calculation, it says V, which is the speed that I want to know, how fast am I going, is equal to omega times r. So it measures omega, how many revolutions per second does the wheel turn, and multiplies it times the radius, which I input. Now if I put a radius that's too small, then that means that my speed that reads is going to be too small as well. So it's going to read a lower speed than the true linear speed. So that's C. Number 7 is C. Alright, a roller derby lady holds onto a rope that is tied to a post. She skates around the post and the rope gets shorter and shorter. If her angular speed remains constant, what happens to the tension in the rope? Alright, well, remember the tension, the force tension is the centripetal force. So I can write it as mv squared over r. Now her angular speed is remaining constant. So I want to write this in terms of angular speed. This is very similar to the previous question. So v is equal to omega r. So this is m omega r squared over r. So that's m omega squared r. So if her angular speed remains constant, then that means that her radius is decreasing, alright, as she goes around this thing. So that means that the tension in the rope is actually going to decrease, C. Alright, which of these arrangements provides the greatest torque? These arrangements provides the greatest torque. B. You have the biggest moment arm, and so it's B. Number 9 is B. Chad stands on a 5-meter long board 4 meters from the pivot point as shown in the figure. He has a mass of 75 kilograms and Kaisa has a mass of 60. Where can she stand to balance the board? Well, Chad has a bigger mass because he's a big guy than Kaisa. So no matter where Kaisa stands, she can't stand here. Alright, because her mass is less and that just wouldn't be enough to balance it. So the answer is she cannot balance the board, which is D for number 10. Calculate the net torque acting on this rod about an axis through the point C, which is perpendicular to the page. Alright, so we're going through this point. Let's first determine if these torques are positive or negative. The torque due to this 25 Newton force is going to be counterclockwise, so this is a positive torque. I'll call it torque 1, and the torque due to this force is negative. I'll call it torque 2 because it's clockwise, counterclockwise. And then the sum of the torques is equal to torque 1 minus torque 2, and the torques are Fr sine theta, so that's 25 times 2 times sine of 45 minus 20 times 2 times sine of 45. So 10 times sine of 45. Oh, I'm sorry, I have a mistake here. This should be sine of 20 degrees. So that's 50 times sine of 45 minus 40 times sine of 20. And I get 21.6. That's 22. It is positive, so that means that it is counterclockwise. So that answer is C for number 11. This figure shows 4 balls, each with a mass of 1 kilogram, attached with rigid massless rods on the corner of a square. Each rod is 1 meter in length. So this is 1 meter, 1 meter, 1 meter, 1 meter. The rotation axis is a point equidistant between the two sides of the square. What is the moment of inertia? So this distance is 0.5 meters, and this distance is 0.5 meters. Alright, so I have 4. I is the sum of mr squared. I have 4 components, so and each is actually at the same distance, so it's going to be 4 times the mass, which is 1 kilogram, times the distance from the moment arm, which is 0.5 meters squared. So it's 4 times 1 is 4 times a half squared, which is 1/4, so that's 1 kilogram meter squared. So number 12 is D. A merry-go-round has a mass of 100 kilograms and a radius of 1 meter. It's spinning at 2 revolutions per second. A kid with a mass of 50 kilograms jumps onto the outer rim of the merry-go-round. What is the angular velocity of the merry-go-round after the kid jumps aboard? Alright, well first we want to figure out what is the moment of inertia of the merry-go-round. It's a disk, and so that's 1/2 mr squared. So that's 1/2 of 100 times 1 squared, 100 kilograms times 1 meter squared. So that's 1/2 of 100, which is 50 kilogram meter squared. That's your initial moment of inertia, and your final moment of inertia is going to be 50 plus mr squared, where this mr squared is the mass of the kid that jumps on the outer rim, and the kid has a mass of 50. So this is 50, which is your initial. That's this value, plus the mass of the kid, which is 50 kilograms, times the radius that he jumps on, that's 1 meter squared. So that's 50 plus 50, which is 100. Alright, so our moment of inertia is increasing by a factor of 2. It's going from 50 to 100. So that means that our speed is going to decrease by a factor of 2. So I can just say right now that it's 2. Our new answer is going to be D, 1. Alright, so that's number 13, D. But if I just want to work through it, I say that L naught equals L final. That's I naught omega naught equals I final omega final. I naught is 50 times omega naught, which is 2 revolutions per second. That's this value. And that's equal to I final, which is this, 100 times omega final. And so omega final equals 1. A horizontal 100 kilogram merry-go-round of a radius 1 meter is started from rest by a constant horizontal force of 50 newtons applied tangentially to the merry-go-round. Find the kinetic energy of the merry-go-round after 3 seconds. Well, I've already found the moment of inertia. In the first one, it's 50, because this is a disk. It has a radius of 1 meter and a mass of 100 kilograms. So the moment of inertia is the same as up here. It's 50 kilogram meter squared. A force of 50 newtons is applied. And I want to find the kinetic energy. Well, the kinetic energy is equal to 1/2 I omega squared. So I need to figure out what is omega. That's the angular velocity. Well, omega is equal to omega naught plus alpha t. Omega naught plus alpha t. But it starts from rest, so omega naught is 0. So omega is equal to alpha t. Well, if I want to find alpha, I know that torque is equal to I alpha, and torque is F times R is equal to I alpha. I'm going to solve this for alpha, which is my angular acceleration. So that's Fr over I. My force is 50 newtons times the radius, which is 1 meter, times the moment of inertia, which is 50 kilogram meter squared. So that's 50 over 50. That's 1 radian per second squared. So that's my angular acceleration. I'm going to take this and plug it in up here. Alpha times t. T is 3 seconds times 1 radian per second squared. That is going to be 3 radians per second. And I take that and I plug it in here for alpha to find my kinetic energy. That's 1/2 times 50, which is my moment of inertia, times 3 squared. See, that's 25 times 9, which is 230. So the answer for this one is D. 14 is D. When swimming near the bottom of a pool, you let out a small bubble of air. As the bubble rises toward the surface, its diameter increases. What happens to the pressure of the air in the bubble as it rises to the surface? The pressure of the air in the bubble as it rises to the surface. As it rises, P is equal to rho GH. So as H decreases, that means that P decreases as well. So number 15 is A. This figure shows 4 identical C-shaped objects. Each rotates about the axis drawn in the thin black line. Rank the 4 objects from the least moment of inertia to the greatest moment of inertia. Remember, moment of inertia is equal to the sum of mr squared. And so the one with the greatest moment of inertia is the one with the most mass at the largest radius. And that is option B. So B is the biggest, and that's because it has this big piece of mass that's at a distance, at the greatest distance from the rotation axis. Now the next one, the next biggest, are going to be C and D, and you see that C is actually equal to D, alright, because it's basically just flipped, but it's the same scenario. Alright, and these are, you still have a lot of mass at a big radius, but you're missing this sidebar like you had in B. And then A doesn't have this piece out here at all, so it has the least moment of inertia. So the largest to smallest is B, C, D, which are equal. B is greater than C, which is equal to D, which is greater than A. And that is, looks like option A for number 16. In a mercury barometer and atmospheric pressure, the height of the column of mercury in a glass tube is 760 millimeters. If the mercury in the barometer is replaced with water, what will be the height of the column? Alright, the height of the column is independent. Oh wait, excuse me. In your barometer, P is equal to P naught plus rho GH. But you remember P naught in a barometer is 0 because it's a vacuum in that closed section. And you see that the pressure is dependent upon the height of the column and the density. So if we replace water, which has a much lower density, if rho goes down, that means that H has to go up. So it's going to be greater than 760. Number 17, that is C. A block of unknown density is floating in a fluid, such as in this figure. Which of the statements about the density of the block is true? The block is more dense than the fluid. That's not true. It would sink. It would be like a rock in water. The block is less dense than the fluid, and that is true. That's why it's floating. The block has the same density as the fluid. That's not true. If that was the case, it would, well, it would just sort of be buoyant. It would just sort of lay there. And the block has more mass than the fluid. That might be true, but we don't know it to be true. Alright, B. Blood enters a clogged artery, as in this figure. What happens to the pressure of the blood inside the clogged portion of the artery? Alright, well, inside, V is going to go up. And then also, due to the Bernoulli's principle, P has to go down. So your pressure actually decreases. V goes up because of the equation of continuity. P then goes down because of the Bernoulli's principle. The block has a mass of 1 kilogram and floats halfway submerged in water. What is the density of the object? Well, we know that the weight, if it's floating, that the weight has to equal the buoyant force. The weight is equal to mass times gravity, and the buoyant force is equal to the density of the fluid, which is water in this case, so it's 1,000, times the volume of the object, Alright, but it's actually floating halfway. So this is the volume of the object over 2 times the acceleration due to gravity. So our g's cancel. Now, we want to find the density of the object. Now we have the mass of the object, and we don't know what it is. And we also have the volume of the object in this equation, which we also don't know what it is. But if we say, since density is mass over volume, we can say that mass is equal to density times volume, and then we plug this in for the mass. So we have density times volume, this is the density of the object, which is what we want to know, is equal to the density of the fluid times the volume of the object over 2 times our g's cancel. Alright, and so our volumes cancel, and so our density of the object is just equal to the density of the fluid over 2. So that's 1,000 kilograms per cubic meter over 2. That's 500. Which is number 20 then is D. The figure shows a manometer which is filled with mercury. The pressure of the atmosphere acts on the left side of the manometer. The temperature of the methane gas inside the bulb is 37 degrees Celsius. What is the pressure of the methane? You don't need the temperature, that's just sort of to throw you off. Alright, so I'm just going to cross that out. First of all, we want to ask ourselves, is the pressure inside the tube less than or greater than the atmospheric pressure? I'll call this P, and I'll call this P naught. Alright, P, because the way that the column is set up, P then is less than P naught. This pressure pushing down is greater because it pushes this column up in this direction. So the pressure inside this bulb is less than the atmospheric pressure pushing down. So then, P then is equal to P naught minus rho GH. Alright, so P naught is 1 times 10 to the 5th, that's 1 atmosphere, that's pascals, minus the density, which is 13,600, times 9.8, times H, which is 0.05 meters. Convert that to meters, 0.05. And then if I put those in, let's see, 1 times 10 to the 5th. Get 93,000. So answer is B for 21. The following figure shows the top half of a pipe carrying water. The standpipes along the top are used to measure the pressure. Where is the pressure greatest? Alright, the pressure greatest is where you have the highest stand of water, so that's A. For the previous figure, which of the following statements best describes the shape of the bottom portion of the pipe, which isn't shown on the figure? Alright, if we have the greatest pressure here, pressure is the greatest there, that means that our velocity is the slowest. So we have slow here, but then we have lower pressure, so it means we have high V here. Alright, slow V to high V. Now, the only way to get that, to go from slow V to high V, is to have a pipe that narrows from left to right. So our pipe is going to be narrowing from left to right. So number 23 is A. This figure shows a hydraulic lift. The force F1 has a magnitude of 100 newtons, and the area is 0.01. If the area A2 is 1 meter squared, what is the weight of the truck? Alright, Pn equals P out, or we'll call it P1 actually, is equal to P2. That is F1 over A1 equals F2 over A2. F1 is 100 over 0.01, and then that's equal to some force, which is the weight of the truck, over 1. So let's see, this is 100 divided by 0.01, which gives me 10,000 newtons. And that's F2. D, and this is A. And note here that number 8 is not A, it is C.